thank you for having me. Yes, always a pleasure to be back at MSU and a pleasure to be back at CTEQ. This is breaking. Come on. There we go. This is actually my third time giving these Higgs lectures at CTEQ. I don't know if I get a special prize. I think Fred will tell me afterwards, maybe. It's always an internal debate about what to include, obviously in 2 hours, and what not to include. So I've done this the last 2 times and have been invited back, so I assume it can't be that bad. But I basically split into 2 parts, almost exactly in the 2 lectures. I think we'll probably get through this one a bit quicker, and this one will take a bit longer. So we'll probably do this one and a bit of this one today. Let's see how it goes. Just so I can get a feel for you guys, roughly how many people would identify as experimental? Like, good. And how many of you would roughly identify as like theory or pheno? Okay, so sort of 50-50. Okay. Good. So I sort of pitched the level at where what I think is a useful information for a particle physicist to know. So, experimental or theorist, that anyone that says I'm a particle physicist should, know this sort of stuff about the Higgs, right? So that's my sort of target audience member is usually one of our own graduate students at UB, who might be an experimentalist who's maybe done a bit of QFT in a particle physics course, but maybe hasn't seen everything. So I apologize if this stuff is a bit too introductory for you. Then you can just relax and have a nice relaxing hour. But hopefully in the second part, there'll be some stuff you haven't seen before. I should also add a health warning at this stage. As I mentioned a couple of times, I mean, I don't want to say I was showing off, but I certainly mentioned that I've done a couple of CTEQ lectures before. This means that I updated my lectures from 2018. So if something seems a bit historical, it is because I was too lazy to update the slide. So I'm only human. And so if you see a calculation and your buddy has done it at 1 order higher, then congratulations, you've got some clever friends. I'm sorry I didn't update the slides. I tried to update the most egregious ones, but I'm sure I missed lots. So I apologize in advance. Please don't be too angry at me. Okay, so without further ado, the Higgs boson. So on the 4th of July, 2012, so rapidly fading in the rearview mirror now, CERN announced the discovery of a new particle, and this was greeted with much fanfare around the world. CBS News said, "Our physics world celebrates Higgs boson discovery." Remember, this was day 1, so CBS already knew it was a Higgs, so they were very on the ball. New York Times, a bit more artsy. They went, "Physicists find elusive particle seen as key to universe." So there you go, linking it to cosmology on day 1 too. We Brits, we're sometimes accused of being a bit reserved, a bit emotionally clipped, and the BBC didn't do us any favors because they said Higgs boson-like particle. Discovery claimed at LHC, so they weren't really putting their money anywhere, right? So it might be a Higgs, it might just be some other type of spin zero particle. It's decaying to vector bosons, so they knew it's not going to be, a fermion. And they didn't really put their money. They were sure, maybe there's something iffy with some of those analyses, so they really didn't go all out, which didn't do us any favors in our stereotyping. Now, sticking with the New York Times, I have to mention that the Higgs was actually discovered as a very, very bad day for me personally. Every other physicist comes, "Oh, it was great, Higgs was discovered, it was press, I cried, it's brilliant." For me, it was a real missed opportunity because this was on the New York Times webpage. And so this picture was taken at Fermilab. They didn't have enough money to send someone to CERN. And so they said, "Scientists at Fermilab in Batavia, Illinois, on Wednesday watched a presentation about the discovery of the Higgs boson, which was shown from Geneva." And so the reason it was a brutally horrible day for me was that if you use the modern technology to enhance an image, that there is me. So close to being on the front page of the New York Times for a good reason, not like, crazy murder stories, but there we go. So close. So it always sounds like that they had to actually wait a long time for this guy to lean forward because this was at 4 in the morning and I was probably just like looking like a zombie. So they had to wait to get that photo. But anyway, so I'm not bitter at all. It's not like 13 years have gone by and I still haven't forgotten it. So it certainly is not something that emotionally scarred me. And then I get to give lectures on the Higgs for years afterwards, so I'm totally over it anyway. Okay, anyway, so moving on. So what is the Higgs from a less journalistic point of view? So the whole idea behind the Higgs is to allow us to generate masses for fundamental particles whilst respecting gauge symmetries. So we have to remind ourselves first what a gauge symmetry is. And so we take some fermion and we ask that if we make the following transformations on the fermion and its conjugate, that we keep nature happy, that we basically give our Lagrangian invariant. And the mass term is obviously going to be off the bat pretty happy with this because I just combine the two phases and they cancel. But the derivative term coming here is what's going to cause the problems. Now, that is fairly obvious because when I take the derivative of the function, I just do a bit of chain rule and I get the bit I like, where the phase would cancel with the conjugate one. But I also get this pesky term here, which is related to the derivative of my phase parameter that I'm trying to make everything be invariant under. So obviously the idea of a gauge theory is to embrace this and to promote the derivative to a covariant derivative where you naturally accommodate for this phase rotation in the definition of the derivative. So now when you define this object and do your gauge transformation, then the phase factor shifts all the way to the front, such that when it pairs up with its conjugate friend, everything's honky-dory, and your Lagrangian is gauge invariant again. So in order to do this, you have to construct a covariant derivative where you take the normal space-time derivative and you introduce the vector field, and the vector field transforms like so under a gauge transformation, and then everybody's happy because the combination of the gauge transformed field and the gauge transformed derivative cancel, so that gauge invariance is manifest. So that's the idea. Of course, if you have a new field, you need to have a kinetic term for that too. So you have to construct a gauge invariant Lagrangian, including both the fermion and the vector field. So you then introduce the field strength tensor, which is this anti-symmetric combinations of derivatives of the field. Then when you do the gauge transformation on the field strength, you're going to get something which is also manifested gauge invariance because this is anti-symmetric and the gauge term is going to be symmetric. So putting it all together, we arrive at everyone's favorite Lagrangian, maybe not everyone's favorite, but certainly one of the top three for most people, the QED Lagrangian, which is now gauge invariant under this U1 transformation that we described. Brilliant. So that's the 5-second introduction to gauge theories. Everything looks good. The important thing is, of course, there's no mass term for the photon. Because if there was a mass term for the photon, and I do my gauge transformation, then I have these yucky terms that are linear and quadratic in my gauge parameter. So the first and very important take-home message from gauge theories, if I want to build them, is don't give me massive gauge fields, right? Because that would be very bad. So then this happens. So then we see the discovery, some historical freedom in how I define the story, but we see the W and the Z. This is the discovery of it at UA1 or UA2. And this has a very, very heavy mass, very much non-zero. And so off the bat, this is a catastrophe for gauge invariance because we have a massive boson and we like gauge symmetries. So how can we combine the two ideas together where we have something which is simultaneously a gauge theory and allows for a massive vector boson in the theory? And that is, of course, how we get to the Higgs, because this is arising from spontaneous symmetry breaking. So the idea, which is a toy example, but the toy example is really nice because it pretty much has everything we need, is to consider just a scalar. So we have a scalar field with the following Lagrangian. We have the kinetic term and the sort of a bit like a mass term, obviously the sign has to be wrong, and a quartic interaction. Now this Lagrangian only has pairs of the field. So when I do my a discrete transformation, I swap the field with its negative, I have the Lagrangian goes back to itself and I have a symmetry. So it has a discrete symmetry from swapping the field with its negative itself. And now if I look at the potential term in detail and get my drawing kit out, if I plot the potential when mu squared is greater than 0, I have something which is quartic, but pretty dull, right? The minima sits there at 0. However, if I allow mu squared to be less than 0, then I get this much more interesting shape where I have a local maxima here, but then two global minimum at plus or minus v, where v is basically just solved from minimizing the potential. Happy days. Now, the point is that what happens when I try to do my field theory is that if I was trying to expand around my vacua here at 0, then I would eventually find things are unstable because I can lose energy by falling down the hill and finding the true global minimum of the theory. So I would like to expand around my lowest energy states when I do my perturbation theory. So instead, I have to expand my field around the true vacua, the true lowest energy state. So if I do that, I take plus v rather than minus v because we want it to have good PR and be positive, not negative. So we expand around the positive minimum, and we introduce this new field eta, which is just a shifted value of phi. And then we put this into our Lagrangian and expand it out, and we get a new Lagrangian, which is in our new field definition. And if we look at the Lagrangian from our Klein-Gordon, which is not usually in everyone's top 3 Lagrangians, like not as good as QED. But if we look at the Klein-Gordon Lagrangian and we look at this Lagrangian, we see that there's a mass term that's now appeared where, because mu squared is negative, it has a real physical value of the mass for this eta field. Now, the interesting thing is that the second Lagrangian, our new eta Lagrangian, does not possess the same symmetry that our original Lagrangian had at first glance, right? So this Lagrangian here, if I make the change eta goes to negative eta, is clearly not symmetric because it has a cubic term there. So, and we can see that from our picture, right? If I'm here and I look this way, I see the same thing as if I'm here and I look that way. Whereas if I'm here and I want to go for a walk, I'm going to go much prefer going for a walk this way because it's a less steep hill, so I won't get so tired. Whereas if I'm trying to go for a walk and climb this mountain here. So when I'm expanding around this vacua, I don't see the same symmetry that I did in the original Lagrangian. However, I haven't changed any of the physics. The whole physics is still given by this total potential here. I'm just changing where I'm looking and where I'm expanding around. So we can be happy that we didn't really break any true physics. We just changed how we are parameterizing our expansion. Good. All right, so that toy model has nearly everything we need to do Higgs physics. We have to make it a little bit more complicated, but not that much more complicated. So the first thing we have to do is to allow for not just 2 local minima, but instead to allow for a continuous set of them. So basically, we have a Friedman here at an angle. We can basically have a set of global minimum related to each other by angles. And to do that, we have to have another direction. So we have 2 fields, phi1 and phi2. Now we want to make our symmetry not be so simple as a discrete symmetry, but instead be a continuous one, which we can do with phase transformation. So now the same thing happens. Now we have a total field, which is written in terms of the 2 complex scalars. We expand them out, and we find the new minimum. Now there's a circle, and the circle is defined with this minimum condition here. So it's just a generalization of what we just looked at before. Now we have to choose our field or how we're going to break the symmetry. So we have to choose the special point which we're going to expand around, and that again is completely up to us. So we choose the phi1 is going to be put basically here, right? So we're going to choose this point here. But again, that was completely up to us. Right now, we didn't didn't have to do anything. We could have chosen any of the points. And then we relate our original field now to our expanded field, where this one is expanded around the vacuum, and this one is just left as a simple scalar. We expand our Lagrangian out, and we have a whole bunch of stuff. But what we see, if we ignore the complicated cubic and quartic pieces, if we look at the pattern of the quadratic terms, we see the psi field here has a no mass term, but the eta field does. So we have one massive state and one massless state. And so this is our first encountering of something called Goldstone's theorem, which tells us that for every continuous symmetry of a physical system which is spontaneously broken, there's a corresponding massless boson. And so for our example before, we lost one symmetry because we could go in this circle around the phi1, phi2 minimum. And so we broke one symmetry, so we get one massless boson, or massive boson. So, okay, that's a pretty clear prediction of spontaneous symmetry breaking. If you're going to break a symmetry, you're going to get a massless boson. So the very first prediction from the using spontaneous symmetry breaking as a tool is that you should see a whole bunch of massless states, right? A whole bunch of massless Goldstone bosons. So the obvious question to ask next is, where are they? And the absorption then is essentially the Higgs mechanism, because obviously we don't see a whole bunch of massless scalars. Okay, so now we want to go to turn the heat a little bit further. So we did a very simple example with just a one-dimensional breaking. And then we did a two-dimensional example. We had a phase rotation as our symmetry that's broken. Now we want to go all the way to gauge theories and break a gauge theory. And so we start with our Lagrangian. We do our gauge transformation. We have to introduce a gauge field to ensure that this Lagrangian is invariant into this gauge transformation, which means we have to promote our derivative to a covariant derivative and include a kinetic term for our gauge boson. So now we have a scalar field coupled to a gauge boson. So this is like a scalar QED now. Good. All right. Now, if we want to expand around our vacuum like we did before, we get the following Lagrangian. Our massless Goldstone boson, our heavy scalar, our weird stuff here. There we go. So here we see something very exciting, because for the first time, we see that we generated a mass term for the gauge boson. So now this gives us something to cling to, because now we have a mechanism for starting off with something which is gauge invariant. Our original Lagrangian has this U1 symmetry. We don't do any naughty things there. But then we choose to expand around a specific vacuum for our the minimum of our potential. So we choose a direction, we expand around it, and then near the vacuum we see this heavy state here. So now by breaking the symmetry, the gauge bosons acquired a mass. So that makes us very pleased. We can even now look at the predictions of the states. We have a massless Goldstone boson, a massive scalar, and now a massive vector boson. We're getting closer to reality. Now we have this term here, which looks pretty yucky because it's a mixing between the Goldstone boson and the gauge field. So what is that? So this is not nothing inherently too wrong with this, but it's not a very convenient term because it's telling us we haven't properly identified the physical degrees of freedom in our theory because we have this mixing. And so we'd like to absorb this into a redefinition of our gauge boson. And this term here is related to the longitudinal degree of symmetry of the massive gauge boson, because we know from our power counting, we know that spin 1 particle has 3 spin states, +1, -1, and 0. And we know that photon has 2 spin states. And so the reason that the photon loses its 3rd spin state is because it's massless. And the Ward density essentially kills the longitudinal degree of freedom. But when I have a massive vector boson, I have to reinstate the longitudinal degree of freedom. And that is missing from my Lagrangian because I didn't redefine A away from being transverse. So this term here is essentially giving us the longitudinal gauge boson piece. And so this is telling us that there's a nicer way of writing our Lagrangian where the physical states are more manifest. And so we can get to that by applying a gauge transformation. So instead of expanding our field like this, which we just did, we redefine our field like this. And if you like a Taylor series, like I do, you'll see that the leading orders in the fields, these are the same. Then when we expand out our fields as before, we see that we are going to identify this, this field here is our Higgs, and this field here is going to be our longitudinal part of the gauge boson. And this is effectively gauge fixing, right? Because what we're doing here is mapping our expansion of the scalar field into a specific gauge choice for our mass for our spin one field too. So writing in terms of these physical states now, we have the following Lagrangian, where we have a massive scalar, a massive vector boson, a cubic interaction, and a quartic interaction for scalar, and then a whole bunch of other interactions between the gauge boson and the Higgs boson. So, so the point is that the other Lagrangian before wouldn't have been wrong, and this choice of field decomposition is essentially a gauge choice. This is, but you don't have to use it, but it makes it at least the physical states more manifest. So you can, if you like doing electroweak corrections, you often work in a different gauge where you have a lot more goldstones and ghost degrees of freedom to include in your Feynman diagrams. But there's pros and cons to different gauge choices, especially at higher orders. So this is the unitary gauge where you see the physics a little bit more straightforwardly, but the calculations at higher order can be a little bit more complicated. So anyway, that's a sort of side point. Okay, so now we essentially are at the Higgs mechanism. I'm jumping around slides, apologize. So we're essentially there. The only problem that's left with our toy example is that we have basically just generated a single gauge boson mass. So at the moment we would say that we can have a massive gauge boson, but it would just be one, right? Because we haven't generated different masses for the Z and the W. So we need to change the gauge symmetry to be more complicated to allow for the fact that we're going to have two different massive bosons in our theory. And so rather than breaking a U1 symmetry, we're going to break an SU2. And so again, we now promote our Lagrangian one more time to be now gauge invariant under an SU2 transformation. So now our gauge transformation is a series of matrices generated by the Pauli matrices, and our fields are these now two sets of complex scalar fields now. So we have 4 degrees of freedom here. Our covariant derivative is essentially the same idea, except for now we have a triplet of fields rather than a single one. And they have a slightly more complicated gauge transformation because it's SU2 is a non-abelian group compared to U1, which is abelian. So this term here is generated because of the non-abeliance of nature of SU2. Putting that all together, we get to our Lagrangian, and we have our usual Higgs potential. This hasn't really changed from the beginning. As now the minimum now is now in this 4-dimensional set rather than a 2-dimensional set. So we have to choose one of our 4 fields to expand around, and so that is taken usually to be the lower hypercharge one down here. Again, we expand in the unitary gauge, same as before, and we focus on the bit that's going to generate the mass terms. And when we put it in, we have, in principle, 3 massive gauge bosons of equal mass. So that sounds pretty good because we have 3 massive gauge bosons in theory, but then we get a little bit sad because we just predicted 3 massive bosons that are the same. So the W mass and the Z mass are kind of the same. That's why I was asking whether you're experimentalist or theorist at the beginning, because 80 and 90 are almost the same number, so maybe they could be the same. But not quite, right? Not close, but no cigar. So the last upgrade we have to do is to change the pattern of symmetry breaking. So what we broke there was an SU2, and we broke it down completely. And so we lost 3 degrees of freedom, and we then acquired 3 massive gauge bosons, but they're all the same. So what we want to do in the standard model to generate the Higgs we know and love is to break a more complicated set of gauge symmetries. So we want to start with an SU2 left and a U1Y, and we want to break it down to a residual U1EM. So this makes us happy because here we have 1, 2, 3, 4 going down to 1. We leave QCD alone because that's not covered by me. That's covered by a completely different lecture. So we have 1, 2, 3, 4 go to 1. So we have 3 degrees of that are 3 symmetries that are going to be broken. So there should be 3 massive gauge bosons. That makes us happy. And what makes us a little bit more optimistic that this might work as a theory of nature is that the residual group that's going to be left over is a U1, which will give us QED because we love QED. Again, top 3 Lagrangian. So we don't want to completely erase QED, but the mixing between these 2 different U1 groups will nudge one of the gauge bosons to be a different mass. That's what we're going to see here. That's the formulas get a bit more complicated, but that's the physics message that we're going to do here. So we relate the electric charge that we know and love to the 3rd component of weak isospin, which is the coefficient of the 3rd Pauli matrix for us in our SU2, and Y, which is the charge of this U1 group here that we start off with. And so we're going to have, because this is an SU2L, this is we're going to assign matter content to either be left or right-handed, and left-handed fields transform as doublets in SU2 left like this, and right-handed fields transform as singlets under SU2, but they still have hypercharge. So right-handed fields live in here, but not here. They're singlets under this one. So for obviously we have quarks and leptons too. Focusing on the leptons, because I think you did a lot of quarks earlier in the day, so it's nice to have a bit of variety. If we start with the leptons, we have a Lagrangian like this, and there's a lot of things to look at. But if you start looking for a term which is quadratic in the lepton fields, you'll struggle too, because there is no mass term in this Lagrangian here. Right? Because our Dirac mass term that we know and love down here, Mr. Me here, if I expand it out, I would write it like this, where I couple left and right-handed fields together. This term here is a doublet under SU2. Right? So this term here cannot be gauge invariant under an SU2 rotation. So the Dirac mass term like this is not gauge invariant under our SU2 left cross U1Y. So we can't start off with a massive lepton in our theory, but luckily the Higgs will do some heavy lifting and give us a way of generating mass terms of fermions too at no extra cost. It's very, very economical. Okay, so now we have to work out what the Higgs sector is going to be. So the Higgs, like before, we had our 2, we had to break a doublet to get our 3 massive gauge bosons. So our Higgs field is going to be a doublet under SU2, and there's going to be one up here with a charge scalar with Q is half plus a half. So, and then down here is going to be a neutral one where Q is a half minus a half, also known as 0. And we do our usual tricks of expanding out in terms of complex scalars. We write down our covariant derivative, which is now getting quite complicated because we have a whole bunch of gauge fields. But once again, just like from slide 1, our Higgs potential remains simple. Right? We haven't done anything. This is our toy model that I started with many moons ago. It never really got upgraded more than the fact that this became more and more complicated and into it. The Higgs potential is the same one that we started off with in our toy example. So by now we do our standard technique, which is becoming second nature. We expand around our chosen vacuum. And then we look at something interesting, which is the following combination of generators that we looked at before, which is given by this matrix here. When this matrix operates on the vacuum, it annihilates it. So this tells us that there is a residual, even after the symmetry breaking, there is a residual symmetry of the vacuum, and that is our U1EM. So the vacuum under electromagnetic transformations is invariant, and this is our surviving U1 gauge theory that we can identify with as electromagnetism. And the So this means there'll be a massless, as a result, there'll be a massless gauge boson, which we can identify as the photon too. Okay, so getting back to now our more and more ugly looking formulas, we have to put in our covariant derivative now, which is a matrix acting on our Higgs scalar field and expand it out. And we get a whole bunch of stuff. But the thing to realize is that there are here the fields W1, W2, and W3, and B are the natural units for the gauge group, but it makes more sense to combine them together into different combinations, which will be the physical W plus and W minus, and then the combinations of W3 and B will make our massless and massive gauge bosons. So we identify this combination as the photon because it has 0 mass, and this combination here is the Z because it has a mass. So we can write this down like this, and then we get our first nice result here. Well, we've got a few nice results already, but we get one of our nicest results so far is that we get a different mass for the Z, and we get a different mass and a massless photon. And if I go back to here, we have a half VG, if we hold that in our heads here, and now we have a half VG squared plus something else. Right. So the most important thing is that the Z, whatever V and G are, is going to be heavier than the W. So already, without having discovered the Higgs, it's done a whole bunch of nice stuff, right? So before, when I was your age, it wasn't known there was going to be a Higgs, right? The Higgs wasn't discovered, and so there was alternate explanations around for electrical symmetry breaking, but the standard model was always the most economical, right? It very naturally gives you a relationship between the Z and the W, which is just well explained, right? So it always had this feeling of that it was inevitable, right? Okay, so before we get onto pheno, we can now look at the fermion mass term, which we highlighted as being not gauge invariant. So we generated masses for the spectrum of gauge bosons, and now we'd also like to know, can we generate the mass for the fermion with a Higgs mechanism too? And so we have to write something which has a chance of being invariant to begin with. So we have to have at least 2 doublets. So we have a fermion doublet here, and then a Higgs doublet and a singlet. So this thing has a chance of being gauge invariant. And then we expand it out. And doing our usual tricks, we get exactly what we want, which is an interaction between the left and the right fields and the Higgs, but also this piece which comes from the vacuum expectation value, which mixes the left and the right fields together and hence gives us a mass too. So at the cost of nothing, the Higgs also allows us to generate masses of fermions as well as gauge bosons. So there we go. So that is the summary of our fundamentals side, where the aim was to remind or refresh our memories as to the theoretical grounding of the Higgs, why we need it in the first place, how it works, and how although the formulas for the standard model Lagrangian become complicated, but the underlying ideas are kind of simple. Right? So that should always be better. When you see the standard model Lagrangian, it's all expanded out, it looks yucky, but the underlying reasons that it's there for is always very nice and beautiful, right? So that should be borne in mind. But the important thing really for the rest of today and tomorrow is this form of the Higgs potential, right? And the parameters in the standard model are basically the Bev, which is our V, and that was related to lambda. So once the V is fixed, which you get from the masses of the W and the Z, the only unknown is the Higgs mass, right? Because that gives you mu squared. So in the standard model, once you measure the mass of the Higgs, you know the Higgs potential. Okay, and so the Higgs gives us our massive gauge bosons, our massive fermions, and now we just have to understand it at the LHC. So I guess I'll just stop here briefly in case there are any questions on that part of the talk. That's all second nature to and we can get on to the pheno. Okay. Okay. Oh yeah.
We often call this Weinberg's law model. Look up Weinberg's paper. The title of the paper is A theory of fermions.
Yep. Yeah, well, that's big. So that paper was preceding the Higgs, right? So that's and then the Higgs mechanism is basically there to fix the mass thermodynamics, right? But yes, that was to allow you to build this left-right model, right? Okay. Okay, so now the remainder of our time together is going to be much more focused on the phenomenology of the Higgs. So how is the Higgs made at the LHC? How does it decay? And what more is there to learn about the Higgs as we go over the next run at the period of the high luminosity LHC, and then in the future towards possible future colliders? So as I mentioned, so you're getting a dedicated set of experimental talks. So these talks today will focus more on the theoretical side of the phenomenology and less on the experimental side. But everything from now on is much more closer to the experiment, right? Okay. Okay, so to begin, I always I put this picture in and I still get invited back. So I don't know how bad a job I have to do before they stop inviting me, because I'm using the wrong PDFs, right? This has to be nonsense, right, this plot. I mean, look at this. Look at this. This should definitely be CTEQ, right? But anyway. So okay, bear in mind that the PDF percentage of this plot is huge and completely unreliable. This shows the production cross-section for various Higgs production cross-sections for the different processes. So on the bottom we have 7 TeV, and then over there in the future maybe we can get to 100 TeV. But either way, it doesn't matter what energy you choose, the dominant way of making the Higgs is always through gluon fusion. So the one we have to be able to understand, and then we'll spend some decent bit of time talking about, is Higgs production through gluon fusion. Then the second dominant mechanism at all energy scales for us of interest is this one down here in the green, which is PP goes to QQ bar Higgs. And this is vector boson fusion up here, which is where I radiate a vector boson on each of my quark lines. They fuse, hence the name, into a Higgs, and then the Higgs pootles off into the sunset. So this is quite nice because we see the top 2 production mechanisms gives us access to the Higgs coupling to the top quark and also the Higgs coupling to the W and the Z. So it will be a much more miserable existence if the vector boson fusion had a much smaller cross section, and we can understand about it. But of course, that's not really the way it works because the top and the W and the Z are around the same mass, so they're coupling to the Higgs. So okay, so it's always going to work out that way, but it's just nice to see. The next one down here, which actually now starts to have some different physics of different energies, is where I do associated production. So I have to take this diagram here and spin it round. So there I have a fusion of initial state quarks. They make an S-channel vector boson, and then that splits into a Higgs and the other vector boson. And now down here at LHC energies, these processes are the next most relevant. But as we go up to higher energies, they become less and less important compared to this species down here, which is the associated production with the top. So that one there is like this one, but rather than going around in the loop, I make 2 tops in the final state. Now at the LHC, that's an expensive process because although I'm colliding at 7 TeV, I don't have to tell a PDF school that I'm not giving all that energy into my my initial state partons because they live inside the proton with its PDFs. So we get energy fractions for our colliding partons that are much smaller, and so this means that a typical collision at the LHC is still reasonably expensive to make a top quark. But as I get to higher and higher energies, the mass of the top becomes less and less kinematically expensive, and effectively they become like massless particles, and I can just produce them with 0 penalty at all. And so this process here becomes more and more relevant as we get to 100 TeV. So if 100 TeV collider is built, associated production is nice because this gives us quicker access to the top Yukawa that we'll see after studying this process here. And then hiding down here is the equivalent one at replacing the top for the bottom quark. And this is already kinematically cheap at the LHC. The bottom quark is very inexpensive for me to make. However, I have to pay the price of having a much lighter bottom quark. So my coupling to the bottom quark is much smaller. So although it doesn't cost me much from kinematics, it certainly costs me in the coupling. Okay. So our the thing we have to understand if we want to understand the Higgs at the LHC is how we can make it through gluon fusion. Now, if you just go and ask your physics buddy in the elevator what the coupling between the Higgs and the gluons is, they'll say, oh, it doesn't couple to the gluons because they're massless. So and then you say, but guess what? I can go through a virtual top quark loop and couple the Higgs to gluons. And then they feel silly. And then, question?
Yeah, I noticed in your previous slide that these corrections are known pretty well in QCD.
Yep.
But now when you add QCD and electroweak, in fact, the only one that you know is PP2X.
Okay, well, you bear in mind my health warning.
Yeah.
My health warning was I hadn't updated the plots.
Yeah, but is there a particular reason why it was so hard, or it seems to me that
okay, that's a very good question. Okay, so I'll try not to give you a flippant answer. So it's a very so okay. So the first thing I should say is that this plot is very much out of date, right? 2014 is a long time ago. It's just very nicely formatted. So 2014, basically prehistory. These PDFs, again, we already established the PDFs, so that's a nonsense. But yeah, so to answer your, so now most of these, so definitely, I mean, this one has ends everywhere now compared to this one here. These ones, this one is still NLO plus electroweak. This one is N cubed sort of in the dry YAM part, so pretty close to N cubed in QCD. This one is N cubed QCD, and then they all have NLO electroweak on them too. So, okay, so that's the updated version of the plot. So now there is much more now. Now your question, if I've not waffled and forgotten it, was why QCD was studied first, so QCD was studied first because the corrections are much larger, right? If when you're doing a higher order correction, you want it to be big, because then you say, look at this important thing I calculated. Is actually there's a no lose argument, because if you calculate something as big, you say, look how big this correction is. If I didn't do my calculation, you'd all be jokers and look, your results are going to be completely wrong. If you calculate it as small, after you spend a day or so crying into your beer, then you say, well, I've constrained the theoretical uncertainty to tiny on this now. So you can always present it in a good way if you know how to do a bit of PR. But the reality is, the QCD corrections are huge, right? So we'll actually see that. Let me come back to that point in a few minutes, right? That'll probably be where I end up with today. All right, so okay, so anyway, so we have gluons that are massless. They couple to the Higgs through a loop. And the first thing we learn about perturbation theory in loops are that they're small unless they're infinity, which they often are. But once we make them not be infinity, then they get suppressed by 1/16 pi squared, which is small. So loop effects shouldn't be the dominant way of producing a Higgs the LHC, right? It should be, if I was just going off my first day of QFT, I would say this one's a tree level process. So it's got to be more important, right? Because it's tree level and the other one's loop suppressed. And so loops suppression is important. However, again, PDFs are very important, as we know. So gluon PDFs at X values that we're interested in, so M Higgs over square S, and the square S being LHC type energies, means that we're basically colliding gluons. So there's so many more gluons in the proton that they completely swamp that minuscule 16 pi squared. They just laugh at it, saying, okay, oh, big deal. And then so that they completely dominate that. And then the Higgs couples to the top is like, you're my best friend. You know, you're so much heavier. So the Higgs coupling to the top is also the biggest too. So those two things are the reason why this process wins out. And so that's why the one that we have to go through painful detail and study. So as I just mentioned, loops are often infinity, right? So the question is this one, right? It certainly looks like it might because it has a low number of particles. So often the low point gauge functions are the Green's functions are the UV divergent ones. So you might worry this one's going to be infinite, but we'll see that it's not. So if you want to think about calculating this as an amplitude, right, what we're going to have is a scalar. So that's nice and easy because that's just an external factor of 1. And then we're going to have 2 polarization vectors for our 2 incoming gluons. And so what I want to do is factor them out and then have this tensor structure here. And then, yeah, I would never realize this because it's way above my pay grade, but if you were smart, many of you are, then you would know that this form of A isn't just completely free because there's a lot of constraints on amplitudes. And one of the constraints is that it has to be gauge invariant, right? So it has to basically have the water density for QCD tells me if I contract the polarization vector with its momentum, then it has to be 0. And so this means that I can use that as a constraint on A mu, and that I have to write down A mu like this. So there's no third term here, which would have flipped indices on the 2 momentum, because that goes away by water density. And then, sorry, yeah, and then actually, I can actually then use it again to eliminate to make it establish a relationship between the 2, and then basically, this is my water density here. Then this sets up the form of the tensor to be constrained. So I have only this leading coefficient here to calculate. So this is nice because now basically what it tells us to do is to calculate B as simply as possible, right? So this is when you're calculating loop diagrams, you nearly always want to make your life be such that you're calculating a scalar quantity, because then you have less tensor reductions to do. And so you usually want to spend the first bit of your time parameterizing your amplitude such that you can extract scalar coefficients as simply as possible. And for us, in our example here, that means I can write down everything with my Feynman rules, and then I can look at the numerator, and I can get a piece that goes like G mu nu. I'm going to get a piece that goes like P nu Q mu, and then I can choose which one I want to calculate, because I know that the total amplitude looks like this. So if one of them looks simpler at the beginning stages, I can just keep that one. And if the other one looks more yucky, I can just use it as a check later on if I'm feeling like I'm going to behave myself that day. So we'll see that one of them is a bit easier to calculate than the other one. I'm going to run out of time in a minute, so I guess I'll get to a good point. It's what on the hour, right? You want me to finish, or you? Oh, okay. It's the next speaker, though. He's a maniac, so he doesn't. I don't want to be chased out of time by him. All right. Okay. So we put everything together. We get a bunch of color factors coming from our QCD vertices. Then we get our Higgs vertex here, which is the MT over V. There's our old friend from the vacuum expectation value. Then we get this loop integral thing here, which is going to be where the money is. This n is going to be our numerator. That's where the tensor structure is going to live. And the d is going to be the denominator. And if you look, because this is my scalar, most of it is propagators, and there's a couple of gamma mu's from the vertex. All right, so we know, or maybe we recall, that when I have a closed loop of fermions, if I follow it around, I'll get a trace in spin space. So I get a trace over my propagators, top propagator, vertex with the gluon with the color stripped off, another top propagator, second gluon vertex, and then the final top propagator. And the denominator is just the 3 propagators together. If you want to simplify down your denominator expression, you can use a Feynman parameterization. This is always a good joke to have with students. You always want to wind up students as much as possible. And so you can tell them, okay, I'm going to use this to simplify it, and then ask them if they think this looks simpler than this. Most people disagree with that statement. But then you can say, aha, but just wait. Because then after that, you can complete the square. So down here, we have our Feynman parameterization of our denominator. So we lump all the momentum terms together into one piece at the cost of integrating over these Feynman parameters. So it looks more yucky. But the nice thing about it is that I can do this rotation such that I basically write it in a Euclidean type way. Right? So if I look at the denominator now, it only depends on L squared. And if I wasn't paying attention to my metric, I would say this looks like it's a Euclidean vector. And then I'm in spherical coordinates. So by doing this Feynman parameterization, I'm able to write it in a way where I can use spherical coordinates after with a small print to do my integral. Now that's the denominator sorted. Now we can tie it a bit further by kinematics, but the important thing now is that we want to get the numerator done. And again, this would take up a lot more slides if I had the G mu nu piece, because that's more complicated. But remember, we did our work at the beginning, and we know that if I just calculate the coefficient of the P mu Q mu piece, I actually get everything. So I can take the numerator, I can ignore all the G mu nu pieces from all my traces and stuff, and just get the piece that looks like this, and it has a much simpler form. So then I'm winning or cheating, depending on how you look at life. So you put it all together, and we get the following loop integral. So we have our Feynman parameters here. We have our shifted loop momentum, which allowed us to complete the square down here. And then we have no dependence on the loop momentum in the top. So this is actually, although it has a lot of terms in it, a reasonably simple integral. We can look it up in the back page of our favorite QFT textbook. Everyone maybe has a different one, but most of them should give you this formula. And for those of you that aren't doing this every day, this epsilon here is a regulating parameter. So we said, okay, often loop integrals are infinity. Infinity is bad as an intermediate step because it's hard to say which infinity you mean, right? Do you mean infinity squared, or do you mean infinity not squared? They're a bit bigger than each other. I wind my kids up with that all the time. Which infinity is bigger? And anyway, so when you're not bullying children, you want to know what to do with your infinity. So what we did was we don't have 4 dimensions here, we have d dimensions, and our excursion from d dimensions is parameterized by this epsilon. So epsilon being 0 is 4 dimensions, epsilon being not 0 is away from 4 dimensions. And if you leave it as vague as that, you can simultaneously regulate infrared and UV divergences at the same time with that. So off the bat, we didn't know whether this was going to be finite or not. But if we look at this term here, the divergences are always extracted from these gamma functions, and gamma 1 is not where the pole is. This is 0 and the negative 1 integers. So this thing here is finite. So I can actually put epsilon to 0. So the good news for physics is that there's not infinite Higgses everywhere, right? This loop is finite and doesn't require any renormalization, which is good because there's no parameter that I could renormalize with it. Okay, so now I can go back to 4 dimensions and get my amplitude. So now I don't have to worry about d being 4. All I have left to do is this integral over my simplifying feature where I added in the Feynman parameters. So now I have to integrate 0 and 1. So now, because this was the most complicated bit, I just put it into some definition and I hide it. And now look, that's really nice and simple there. So that's how you do the magic. Just put it under the rug. Nice and under the rug. Good. So now the reason being that I can actually just put that into Mathematica. Right? That's the sort of Mathematica integrates things much better than me. So I just type this integral in, and I know the value of the parameter, right? And then I plot it for this s. So s, the denominator here, is m Higgs divided by mt squared, which is here. So this thing here is the Higgs is much, much lighter than the top, and up here, the Higgs is much, much heavier than the top, right? And what if we think about where the bit down here, if we zoom in, we actually see that it's a really slowly growing function, right? So we start up here at a 1, and then if we go all the way to the Higgs is equal to the top mass, we get a 14% correction. But it's surprisingly close to 1. And if I look at where the physical values are, so okay, this is helpful if you know what the answer is. But if I look at where the Higgs mass is here, I see that my correction from the top mass away from 1 is only about 5%. So what this is telling me is that if I went back here and sort of replaced this with a 1, I wouldn't be doing that bad a job. Maybe I wouldn't get paid megabucks. I'm not going to be retiring too soon, but I'd probably be enough to survive, right? It's a 5% correction. So if I'm allowed to have that sort of uncertainty, I could ignore this and just look at this sort of thing here, right? And what that effectively is saying is that I can integrate out the top and make a situation where the Higgs is infinitely lighter than the top, which is putting me down here, and have an effective field theory. And so that's a good place for me to draw a line for today. I told you it's going to be a bit of a random spot where maybe I warned you it might be. So tomorrow we will look at how to do this a little bit more formally and to identify the effective field theory where the top is going to infinity. We'll also discuss why that's useful, because you could just say, oh, well, why? You know, if I just calculated Mathematica a minute ago, why do I now want to discard it? It just seems sloppy, but we'll talk about that tomorrow. The interesting thing too, though, just to take home as a thought, is that if there was any heavy fermions out there, they would have scaled linearly with this, right? So as soon as you measure the Higgs cross-section as being close to 1, like close to the prediction of the standard model, you can immediately say there's no more heavy 4th generation quarks that look like a copy of our standard model. Right? Because if there was, they would just blow up the Higgs amplitude in the same way, right? There's no dependence on the top mass here, right? So I just add them in, right? And so the fact that so from within a few months of discovering the Higgs and seeing that the cross-section was indeed close to the standard model value, that immediately caps any notion of there being a 4th generation of quarks, right? Now, of course, you can add in heavier fermions, but they won't be exactly the same as the standard model. And they won't be the same as the like a top quark, right? Because it would just grow linearly like it. So good. Okay. So that, I guess, is where I'll finish today. And then tomorrow we'll continue discussing in that direction. So thank you for your attention. I guess I have time for questions before. Sorry. You're too kind. I don't think we deserve it.